Hi everyone, so welcome to the next lecture. So just a quick recap of where we are. We started the course with the transformer architecture, right? And we went quite deep into it. Also understood things like self attention, cross attention, positional embeddings in quite a bit of detail, right? Then we understood the task of language modeling and then saw how to use a transformer for modeling this task, right? And then we noticed that, or we made the observation that there are three types of models which are possible, which is encoder only models, decoder only models, and then encoder decoder models. Here we looked at GPT, sorry, and when we were looking at GPT, we also looked at decoding strategies in quite a bit of detail, right? So GPT combined with what happens at the output side on decoding, right? When we are looking at encoder models, we looked at BERT, and along with that, we also looked at tokenizers in detail. So BERT and then combined with what happens at the input side. Of course, both of these, what we saw in the context of GPT, that is decoding strategies, and what we saw in the context of BERT, which is tokenizers, these both are model agnostic, right? So the same ideas hold for any language model that you are looking at, right? And today we are going to look at encoder decoder models, and which is BART and T5, right? We will make a small detour and talk about GPT-2, right? And that is sort of to motivate some of the choices that affect performance, and then from there on go to the model for T5, right? So today we're going to spend a lot of time on this, which is the choices that affect performance, and then based on those studies that we will talk about, we will arrive at the model choices that were made for T5, right? So that's the overall setup for today's lecture. So with that background, let me just start. So if I'm going from BERT to BART, so we'll not spend too much time on BART. Our main goal is to go to T5. So BART is an encoder-decoder model, and T5 is also an encoder-decoder model. But nothing much to say here. So we have looked at BERT and its variants, GPT and its variants. Uh, Two different approaches we have looked at. So what we found in the literature and is that BERT is good at comprehension tasks like question answering because of its bidirectional nature, and GPT is good at text generation because of its unidirectional or the causal way in it, because it's just trained to predict the next token. So that's exactly what text generation is about, right? So why don't we take the best of both worlds and look at encoder-decoder models. And this diagram is actually quite familiar to all of you because this is the original context in which we had studied transformers in great detail, where we had an encoder, we had the self-attention, then we had the decoder, where we had the masked self-attention and the multi-head cross-attention, right? So this is quite familiar to you. So BART just uses this encoder-decoder model, and it is trained with an objective where you mask certain continuous spans in the input and you try to predict those spans, right? So as I said, I'll not spend too much time on BART because whatever I want to say about BART, the objective function, etc., we'll all cover that in the context of T5, right? So this is just, you can think of this as the initial encoder decoder model, right? And this lecture actually is interesting. It's a good point to say this. So BART was a model which came out of Meta. Then GPT-2 is of course OpenAI, and then we have T5, which is Google, right? And all of them came about roughly around the same time, right? Roughly around the same time, and with again similar ideas like prompt. The idea of using a prompt and prompting large language models was there in GPT-2. It was also, I think, there in a few previous papers. And then T5 also had a lot of ideas which were based on like prompting the model to do everything, right? Converting everything to a text-to-text transfer task. So all of these came together. So very similar ideas. So I'll cover all the ideas, but not necessarily in the context of every model, right? So by the end of this lecture, you will know all the ideas that are important, but not necessarily in the context of every single model, but overall I'll cover them, right? So that's the way the lecture has been set up. So this was an encoder-decoder model. And let's look at what the architecture looked like. This had a GALU activation function. Very, as I said, this is the basic model that you had seen in the context of original transformers when we had done. and then the input sequence is corrupted, as I said, right? So this input sequence is corrected, and it's done in multiple ways, right? Either they use random masking or token deletion or document rotation and so on, and that the encoder takes in the corrupted sequence and the decoder predicts the entire sequence, right? So you can think of this as some kind of a denoising autoencoder where you have an input which has been corrupted, sorry, I keep saying corrected. So the input could have been, the original input could have been the boy sat on a chair and watched TV. Now you could corrupt it in different ways. You could drop the face sat on a chair and replace it by mask, right? So that's what random masking is, or you could delete certain tokens. And then you have this corrupted input and you're training the model to take this corrupted input and predict the full sequence, right? So at the output, I would want to predict the sequence which was originally there, which was the boy sat on a chair and watched TV, right? So this entire set of all these 8 words or 9 words I want to predict, when at the input I was giving just a subset or a corrupted input was provided to me, but I have to predict all of this, right? So that's the objective that they use. So it looks similar to a denoising autoencoder where you have an input, your model is trying to regenerate the input, but then the input has been corrupted, some noise has been added to it, and you are trying to generate the original input from the corrupted input, right? So that's the idea, right? So that's all there is to say about BART at this point. Oops.